All right. Well, good morning, good afternoon, or good evening, depending on where you are in the world. This is Dave from Element 14. I wanted to welcome you all to today's presentation with Texas Instruments, where we'll be discussing DC-to-DC power solutions for FPGAs and data converters. And today we are grateful to have Michael Hemlinger, an applications engineer from TI, who's going to walk us through today's presentation. So before we turn it over to Michael, just a few administrative things. If you have questions for Michael throughout the presentation, please do so please ask him by using the Q&A applet located on your WebEx screen. We're going to go through those at the end of the presentation and answer those questions, or as many as we can, given the time allotted. Now, if you have questions later on, or we don't have time to get your question answered, please make sure to post those questions on the event page that you registered from on the Element 14 community. If you have any technical issues, you're having a hard time hearing or seeing the presentation, you can feel free to chat me directly at Premier Farnell Webinar using the chat function of the WebEx, and we'll be happy to help take care of any issues you may run into. So without further ado, I'm going to turn over to Michael Hemlinger, who's going to take us through today's presentation. Michael, take us away.
Okay, thanks for the introduction. So welcome everybody. Thanks for joining the session. Today's topic is the DC-DC power solutions for the FPGA as well for the data converters or ADCs. Yes, so I'm Michael. I'm working at Texas Instruments as an application engineer since a few years, and this is mainly in the range of the low power DC-DC converters. Okay, so this here is again the abstract. I think you saw that already about more detail of this topic. And the agenda for today for this training is the first main portion is about the FPGA power supplies or the power considerations. So how to estimate the current requirements, then which different system architectures we have. Then we talk about the FPGA rail requirements. We will also have a look on different sequencing options for the different rails. And as well at the end of this part, we will have an example calculation on our new 62135 DC-DC converter. After that, the second part, we will talk a little bit about powering ADC and data converter, and this is mainly also a comparison between LDO and DCDC about the performance of the ADC and data converter. And at the end, as already mentioned, we will have a Q&A session, so please feel free to just send the questions through your WebEx, and we will try to answer all of these questions at the end. Okay, so with this, let's get started with the first chapter. So what we can see here is, let's say, typical FPGA supply rails. So of course there are more rails than that, but I think these are, let's say, the main rails. So for example, we have, of course, the core of an FPGA. And as I said, this is just an example. So many of them have a voltage range, let's say, or target of 1.2 volts. Then we have also as well some analog inputs, analog rails. So they are, for example, in a voltage level of 2.5. Then we have some I/O rails, and this is also depending then on the application. So this could be between 1.5 volt up to 3.3 volt. And we can have auxiliary supply rails. In this case, as an example, also 1.2 volts. So to supply these different rails, of course, we need some DC-DC converters. And we have on the left side an intermediate rail. And this is also depending then on the system itself. And for example, typical intermediate rails are 3.3 volts, 5 volts, or as well 12 volts. So our next question is, at the beginning of FPGA design, what are the current requirements? And for this we can have a look on the next slide. This is mainly dependent, let's say, on the FPGA itself, as well on the system or on a specific usage which is running on the FPGA. So there are different ways to get the current requirements or the current values. So one option is to go to the TI page. So we have a WebEng FPGA power architect where you can look into. So there are a whole bunch of different FPGAs you can select, and then you can already estimate the current consumption you will have in your system. Also, the other option is to go directly to the FPGA vendors. In this case, for example, Xilinx or Altera, one of the famous ones, and they also have called power estimator tools to get more clear numbers which current requirements you will have in your system, in your application. Okay, so beside of the current, of course, we saw it on the slide before, there are different options for the intermediate rails. And these different options have advantages and disadvantages. We can see it here. So I think it's mainly dependent on the main power supply. So one option is, for example, if you have a 12 volt or 24 volt source, then it definitely makes sense to go down, for example, to 5 volt or 3.3 volt intermediate rail. But in other cases, for example, you have 48 volts, it's the main supply, you can go down to a 12 volt intermediate rail. Below you can see here in the table, the advantage, for example, for a 12 volt intermediate rail is that we will have the lower input current on the DCDCs. The disadvantage is that the efficiency of this converter from 12 volt down, for example, to 1.2 volt, this will be definitely much lower. If we have a 5 volt intermediate rail, the efficiency is definitely much higher, and the disadvantage here is the input current compared to the 12 volts will be higher. The same, or almost the same for the 3.3 volts. So we have really high, almost highest efficiency or high efficiency, but as well a disadvantage here compared to the 12 volt will we have the highest input current on these rails. So again, depending on the application, on the main supply, we have to think about it, which intermediate rail we want to address, and then we can go for the next steps to select the right DCDCs for each rails. On this slide we can see again the typical rails of an FPGA, and again the voltages, for example the core, analog, I/O and auxiliary. And now there are also in the next column the tolerances. So these tolerances, normally you can find it in the data sheet or on the application notes of the vendors. So you can see it on the bottom side of this slide. You can see an example of an Altera Max 10 FPGA. There you can see the different voltage rails and then the tolerances as well as the voltage levels. So for the analog I/O auxiliary, the normal case, I think, for a lot of FPGAs, the tolerance is 5%. For the core supply voltage, in this case 1.2 volt, there are different tolerance specs. So there are some with 5%. On the bottom example for the Altera, I think in this case it's 4%, but there are as well some FPGAs out with really tight tolerances down to 3%. And this is definitely challenging for all DC-DC converters to achieve this, of course. As well, we can see here requirements for the different rails about the transient performance. So you can see here, for example, the spec is 50% of the maximum load, and the slope of the transients are faster normally than 1 amp per microsecond, or faster than equal 1 amp per microsecond. And then as well, it's also quite important in some applications, of course, the sequencing order. So this should be also stated in the data sheets of the FPGAs, and then there are several different options how to do the sequence, but we will have a look later on. On the next slide, we have now more details about the voltage tolerances. So the power supply performance consists, let's say, about two different operating conditions. So the first one is a statistic one. We can see it here, it's in the middle. So we have the nominal output voltage. On this nominal output voltage we have the voltage ripple of the DC-DC converter. And here we have now, let's say, fixed or gradual changes. So these are the DC variations of the DC-DC converter. Beside of that, we have the dynamic changes. You can see it here. So these are the quick changes, also called AC variations. And these are then on top of the DC variation. And you can see it here, for example, we have the nominal voltage then, and we have, for example, plus and minus 5% of the tolerances of this FPGA rail, power rail, for example, the core rail. And what you can see here as well, if we have calculated DC variation, for example, then up to the maximum tolerance, we have some margin then for the transient of the DC-DC converter. So let's begin with the static changes. So the output voltage accuracy, DC-wise, there are several parameters which influence this accuracy. So the first, you can see it also in the picture on the right side. The first is the feedback voltage accuracy. The next is the feedback divider tolerance. So depending on the resistors itself, it has a big influence. If you use 5%, 1% or the 0.1% resistors, this will influence, of course, the output voltage accuracy. And on the top of that, we have also called load regulation and line regulation of the DC converter. And this information you also can find it in the data sheet. Here's also an example. So all of these parameters we have to include and think about if we want to calculate the maximum output voltage accuracy. If we want to calculate it, we have here a simplified equation. So this equation gives the maximum output voltage accuracy in percent. So what do we have here? We have TR, I call it TR. This is the tolerance of the resistors in percent. We have the feedback voltage. This information can be found in the data sheet. Then we have the output voltage, and of course this is the output voltage. You set the DC-DC converter for the FPGA rail, and we have the T feedback voltage. So this is the tolerance of the feedback voltage, also in percent in this case. So this is quite an easy equation. Just put the values in, and then you get immediately the maximum DC voltage accuracy of the selected DC-DC converter. And on the top of this result, you have to add the line and load regulation from the DC-DC converter as well. On the bottom side, you can see a link. This is an application note where the calculations are in. So if you're interested in more details, you can just have a look. Okay, here I will show some examples. So again, same equation. And then, for example, we have a look at example 1. These are resistors with 1% tolerance. We have the DCDC feedback voltage tolerance of 2%, a feedback voltage of 0.8 volts, and an output voltage of 1 volt. And this results in an error of 3.1%. The second example, we're using 0.1% resistors. The feedback voltage, output voltage is the same, and this results in a 2.1% accuracy. Then in the third example, we have different output voltage and different feedback voltage. And the same as in example 4, we have then again different output voltage, different feedback voltage, and 0.1% resistors and a 1% feedback voltage tolerance. So you can see all of these parameters have an influence on the total DC tolerance. So mainly, if we choose a DC-DC converter, the feedback tolerance is fixed, the feedback voltage is fixed, and also the output voltage is somehow fixed. But of course, we can definitely have an influence on the tolerances of the resistors. So using 0.1% resistors is definitely a good starting point to get the highest DC accuracy. And in these examples, we can see the example 4 shows now the best accuracy. It's 1.1%, and if we have a total tolerance of 5%, of course we have now here the highest margin for the AC tolerance. So for 5% we would have 3.9% of tolerance for the AC, for the transient. So looking forward, what else do we have in the static behavior? So for the DC behavior, we have some influence of the DC loss. Not from the DC-DC converter and FPGA, it's more than the wires and the PCB itself. So there are 3 different options. So one thing is there are some of our DC-DC converters have sensing pins where you can directly sense the voltage at the FPGA input. Due to this, you have a better regulation, of course, and you have exact right voltage at the FPGA without any voltage drop. The second option, of course, it's always recommended to use wide and thick copper traces to get less DC resistance and to get less voltage drop. And the last option is to place the power supply really close to the FPGA rail. And this is, I think, really a good option as well for our product lines and our products. We have really small modules and also small discrete solutions, and this offers you the chance really to put it really, really close to the FPGA. Here, short information about measuring the output voltage. I think this is, common knowledge, but again, in some cases, it always helps, because if you want to measure the output voltage for the ripple estimation as well for the transient performance, it's always good to use, it's called a tip and barrel measurement on the right side, to have short ground connections, because on the left side with a bad measurement option, due to this longer ground connection, you will have, or you create an antenna, and you can pick up radiated noise, and this will influence your measurement. So it's always good, if you want to have accurate measurements, always use the right measurement method with the tip and barrel. The next step now, after the DC accuracy, let's have a look on the dynamic one, on the AC accuracy. We have as well here some different influencing parameters. So mainly it's, of course, the low transient performance. And in the low transient performance, the behavior is depending on, first on the slope. So you can see on the right side an example. As we saw before, this is in the requirements of the FPGA vendors. It's mainly faster than 1 amp per microsecond, the slope of these transient steps. The second parameter which has an influence, it's the step size, of course. So there will be a difference if you only have a step size from 0 to a few hundred milliamps or from 0 to a few amps. So that's the second influence. Then as well, the converter topology itself will have influence on the transient behavior of the DCDC. So there are different ones, for example, the voltage mode, the current mode, and then we have hysteretic converters and DCS control. And especially the hysteretic and DCS control, these type of control topologies offers the best transient performance you can get. So we are really, really fast, and with this, of course, you can achieve really to keep or to stay within the tight tolerances of these FPGA supply rails. And at the end, also the output filter of the DCDC has an influence. So depending on the L and C combination, or mainly on the output cap, this will have definitely an influence how the output voltage accuracy is during the transient behavior, during the transient steps. On the next slide, we will have a little bit more detailed look on the transient behavior. So again, it's affected by the load step size, the speed, so the slope, and the output capacitance. And if you have a detailed look here on a power supply, we have the output capacitor. And the output capacitor consists mainly of course, the capacitance. Then we have parasitic, or let's call it parasitic inductance, or equivalent series inductance, and we have as well the equivalent series resistance. All this is in the output capacitor. So if you have a look on the load step itself, the voltage drop looks, let's say, similar to this picture you can see here. And during the load step, and depending on the slope and the type of the output capacitor, you will have at the beginning, you will see the main steps due to the ESL. Between these ESL steps, you will see a drop of the ESR, and after this, you can see then mostly the behavior of the real capacitance. And this is always the time when the device or the rail is back on regulation after this transient. This will also be a little bit different depending on the type of output capacitance. So using a ceramic cap with a high speed or high bandwidth converter, you will probably not see this behavior that much. But if you have a really high current converter, let's say up to 10, 20 amps, and you're using really big bulk capacitance on the output, I think you will see this effect more clearly. So if you have a look here, we can have a look now on the complete system. So on the left side, this will be the, let's say, the main power supply or the main rail. Then we have the DCDC power module, and then you can see we have different stages of the output caps. And first, normally you can place a low frequency bulk cap. After it, you can place mid-frequency and high-frequency decoupling caps, and in some cases you have really a cap on the die of the FPGA. And this is quite important, and to have a really good decoupling network, and of course for the really high transients, it's highly recommended to use good ceramics like X5R and X7R dielectrics. So you can see also on the top right side some different types of capacitor, but I think it always depends on the current requirement of this rail. But clearly for the high frequency decoupling caps, it's always recommended to use just ceramics. If we can use for this FPGA power rail a DC-DC converter from, for example, the TPS62K family of TI, then normally we don't need the big bulk capacitance anymore, because these devices are very, very fast of the bandwidth. So normally we only need small, mid and high frequency decoupling caps on the output of the converter. And this of course saves space and as well the cost of these big bulk capacitance. Then few words to the sequencing stuff. So I think there's different requirements. So one of it could be you need monotonic sequencing or monotonic startups of the different rails, or you want to change the startup time, or in other cases you may need, beside of the power up, you also need some special power down sequences. And from the techniques, I mean, one easy option is always you can use an RC filter, for example, on the enable pin to provide somehow sequence, but it's better to use, of course, if the device have one, a power good output. This is only always quite easy to use, but again, this is only possible for the power up. And at the end, what have the most features, I would say, it's to use a special sequence controller. And this one, you can also use it for power up as well for power down. One example is the LM3880. So you have 3 outputs for this device. So you can control 3 different devices, or let's say you can have different flags for different sequences. And you can choose the order of these outputs. You have a delay, and if you want, you can use it as a daisy chain if you need more rails. So I think if you have more rails, it's always, I think, more convenient to use such kind of a controller, because you're much more flexible and have much more options to control these different flags. Before we go to the live, let's say, calculation or example calculation, here again, just recommended steps from TI. So if you're starting with your first design of FPGA, you always can try first to go to the vendor and check out what are the current requirements and which rails do you have. Second good options then to check on the TI page, on the TI reference designs. There are really a lot of them, and in some cases it's really easy just to take this reference design and you have already the complete power supply structure for your FPGA. And the last step, also you can check on Webbench. There are a lot of tools you can use in the FPGA Power Architect, which helps you to get the right design and the right DC-DC converters to power your FPGA. All right, so now let's go to the example calculation. So I want to do it with the new 62135, and this is a quick overview on one slide of this new device. So it's a 3 to 17 volt input 4 amp buck converter in a 3x2 QFN hot rod package, so it's a really small package. And if you have a look on the feature list, I highlighted the main features here which are important for FPGAs. So we have a huge Vout range, and now here in the red circle, these are really the main things. So we have a ±1% feedback voltage accuracy over the entire temperature range from -40 to 125 C of the junction temperature. So this is really important to get this good DC accuracy we saw before. The second thing is we have a mode pin, so we can force the device in a forced PWM operation, and with a high frequency of 2.5 megahertz. And this device also uses the DCS control topology, which helps to get really, really good transient performance. Besides of that, this device can support high output capacitance, and we have additional features like output voltage select. So if you need different output voltages, you can change it on the fly during operation between two output voltages. We have adjustable soft start and a tracking function, and as well 100% duty cycle operation, and overcurrent protection, and as well power good and output discharge function. On the benefits, it's really the small real package, and as I said, the huge feature list for this small device. On the next slides, we can see here some information why this PWM is so important. So the first thing is the accuracy I already mentioned. So this is a cutout of the data sheet. So if you have a look here, the feedback voltage accuracy in the PWM mode over the entire temperature range is -% from -1% to +1%. And this is really mandatory to get this high accuracy DC voltage. Besides of that, you can see here on the bottom then the comparison of the load regulation. On the left side, this is in PF power safe operation. On the right side, it's in forced PWM operation. And you can see a clear difference on, especially on the light load, the output voltage accuracy is much less compared on the right side if the device works in PWM mode. So this is again also a huge advantage and helps, of course, to get really or to keep the tight tolerances. On this side, just wanted to highlight again the small solution size as well as the small size of the IC. So this is a cutout of the evaluation module which is available on the web. So you can see here the IC U1, it's a 2x3 millimeter device, and you need only input capacitor of 10 microfarad. So this is 0805 capacitor. The same for the output capacitor. In this case, is a it's also 10 microfarad 0805. And then we have just two resistors to adjust the output voltage, and the C3, this is the soft start capacitor. And the solution size on the EVM, it's below 60 square millimeters. And if you use a chip inductor, small chip inductor, for example, 0805 size, and small components like the resistors and the soft start capacitor as 0402 size, then you can go down below 40 square millimeters, which is really, really small. And this, of course, helps you to save space and place the IC fairly close to the FPGA rail. So let's start with the calculation. So let's use the core rail. So in this case, we want to have a DC-DC converter with an output of 1.2 volt. And in this example, we want to have 4 amp of maximum current for this rail. The tolerance should be 5%, and also the transient should be 1 amp per microsecond. On the intermediate rail, I choose now, since this is a high VIN device, I choose an intermediate rail of 12 volt. So we need a DC-DC converter from 12 volt down to 1.2 volt, which can support 4 amp max. And this is possible with the 62135 device. So if we start the calculations, we can start with the step 1. And the step 1 is we set the output voltage to 1.2 volt using 0.1% tolerance resistors. So if you have a look on the top right side, we can see the data sheet. cutout of this device. So the feedback voltage is 0.7 volt, and I choose the resistance values to 130 kilo ohm and 180 kilo ohm. And with that, we can get an output voltage of 1.2 volt. So this is the first step. The second step is we calculate the maximum error of the output voltage, DC. So we can also have a look on the top right side again in the datasheet, and there we can see if we operate the device in forced PWM mode, we have this 1% accuracy. So the TR, the tolerance of the resistors, oh sorry, there's something missing. I apologize for this, it was too fast. So the assumption was we have 0.1% of the resistors, and we have 1% of the tolerance, the feedback voltage. And this results in an error of 1.08% using the equation on the right side. Then we have the step 3, we add the load regulation. So assuming we need the full power, we can also find in the datasheet the load regulation. In its PWM mode operation, we have 0.05% per amp. So if we have this number and we need 4 amp, we have 0.2% in total, and this will result then in a total error of the DC accuracy in 1.28% at full load. So this is the calculation of the DC accuracy of this device with this output voltage. On the next slide, we see now the calculations or the measurements for the AC accuracy. So again, if we have now the maximum DC error of 1.28% and we have a total tolerance of 5%, we will have a 3.72% margin for the load transient behavior for the AC accuracy. And you can see here now on the bottom left side the first result. So this is the 62130 EVM with an output voltage of 1.2 volts and a load step from 0 to 2 amp. And the red lines are the limit lines for its plus and minus 3.7% and the nominal 1.2 volt. And the resolution here for the output voltage is 50 millivolt per division. So you can see we are still in the tolerances, but it's really close, let's say. On the right side, I did again another measurement and adding additional 47 microfarads, and you can see now we are definitely within the tolerances, within the target of the spec of the FPGA core rail. All right. Okay, so these were the calculations. Here, a short overview, which options do we have from the power supply itself again. So the 62135 was a discrete solution. The advantages here on the right side, we have a little bit more flexibility, and we can optimize the design conditions because we can choose the capacitors, inductors, so we have the big flexibility. The total cost will be a little bit lower. Also, the thermal performance will be better because we can spread the heat better on the PCB, and also we can still achieve a small size, as I also showed before. The cons are, okay, it requires in some cases more design time, and the bill of material count is higher. And on the left side, I think it's quite nice to go with a module solution. The advantage is clearly the cost of the ownership is lower, and of course the components are less. And yeah, depending on the experience of the engineer, it takes you less time to provide this complete power solution for your FPGA supply for the FPGA rails. And of course, with the module approach, you can really achieve the smallest solution size total. But again here, the negative aspects, it's more expensive and maybe it narrows down the operating range. This, for example, is also a quite new part, the 82130. So you can see on the bottom right side a nice picture of it. So there's on the top of the IC itself, there is the inductor. So you can save at least the PCB space, which normally takes for the inductor. And this is also up to 17 volt input voltage range converter. This can also support up to 3 amps. So this is a really nice solution if you want to go with the 12 volt intermediate rail. Also here, maybe if you can have a look on the presentation afterwards, this is a really nice overview for all the different models we have here from TI, which are really nice for FPGA power. And we have completely different input-output voltage ranges as well, for starting with 1 amp output current up to 30 amp of output current. So that's quite a big portfolio here. Okay, so the second part of the presentation is now the powering the ADC and data converters. So I think as you or many of you know, the electric performance of the ADCs or general data converters depends mainly on the cleanness of the supply voltages, mainly on the analog supply. And I think in the past, and it's still there, LDOs normally are used to supply these, at least the analog voltage supply rail. But of course, you know, the efficiency of LDO normally is fairly low. What I want to show is that using a TPS62230 DCDC converter, it's really a nice choice to combine then highest efficiency for the DCDC, but still with really good performance of the ADC or data converter. What we have for this, you can see it here. We have an existing reference design as well on the web, so you can just click on the link provided here, and also some documentations on the link of the test results. And the reference design, it's based on a 500 MSPS ADC, it's a 12-bit, and we were using, you can see it here on the bottom side in the schematic, we are using 2 switching power supplies and generating the right output voltages, and on the right side we added some filters. In this case we added ferrite beads and some small additional capacitors. And we can see now on the next slide a nice comparison between LDOs, so powering LDOs, the ADC, compared to the SMPS. So the blue lines you can see here, these are the performance of the LDOs. The orange, it's the performance of the switch mode power supply, 62230. So starting from the top left side, we can see here the performance of the signal to noise ratio. And we have, in this case, for example, 3 different signal frequencies. And yeah, as you can see here, there is really small difference between the LDO compared to the SMPS solution. On the right side, we have the results for the SFDR, and here it's a little bit different, but still, depending on the frequency with the DCDC, we still can achieve really nice performance compared to an LDO. On the bottom left side, you can see now the big difference, of course, in the input current consumption. So the LDO, of course, has, compared to the DCDC, it's almost a double of the input current consumption compared to the switch mode power supply. The same, of course, then for the efficiency. So the switch mode power supply 62230 can achieve, in this case, almost a double of the efficiency compared to an LDO approach. So I think this is really nice, and also I think for the future projects, we think that's coming more and more, because you need to get better efficiency to get the power down, and as well this helps, of course, as well for the thermal performance of the complete application. All right, so I'm almost on the end. Here you can have a look then on additional resources. So we have here the modules page, then complete the overview of the power from TI, as well the resources for the FPGAs for Xilinx and Altera on the TI page. And we have here the Webbench FPGA Power Architect and link, and as well our search bar for the FPGA PowerD reference designs from TI. Okay, with that, I would say thanks a lot for your attention. And now, if you have any questions, please feel free. And I'm not sure, maybe I think you should just type it in, and then I will try to answer it if there are any questions. So thanks again for your attention.